It's time to learn about continuity. We've already talked about limits, and we're going to use these to give continuity a formal definition. We're also going to see that continuity is a useful tool for evaluating limits. Intuitively, a continuous function is one whose graph you could draw without lifting your pencil off the paper. So this, for example, is the graph of a continuous function. On the other hand, this one isn't, since you need to lift the pencil off the paper to jump from the part on the left to the part on the right. This is another discontinuous function, since we need to lift the pencil to draw the point up here. We could easily make this particular function continuous, though, by moving this point down to where it in some sense should be. Where it should be is determined by the limit, and this is how we define continuity. A function is continuous at a point A in its domain if the limit of f at A is equal to f of A. When we call a function simply continuous, without referring to a particular value of A, we mean that it's continuous at every point in its domain. This definition, for the most part, justifies our pencil and paper intuition about continuity, since through the entire process of drawing the graph, we're approaching the value that we're about to draw. But there's one subtle but important point that we've missed. Let's look at the graph of 1 over x. This looks discontinuous, since we've got two separate parts, one on either side of the y-axis. But the x value separating these pieces is 0, and 0 is not in the domain of f, so it doesn't have any effect on continuity. Remember that continuity is determined entirely by how f behaves on its domain. So 1 over x is actually continuous. The apparent discontinuity is really the result of a gap in its domain. Likewise, this function isn't continuous, but if we remove 5 from the domain, creating a gap, then the function becomes continuous. It's a subtle point, but it's important if you really want to understand continuity. So let's take a look at the original discontinuous graph on the left, and the one that has the hole filled in and is therefore continuous on the right. Their values at 5 are different, but remember that values at 5 don't affect limits at 5. And since these functions are equal everywhere but 5, they have the same limit there. The great thing about the function on the right, however, is that the limit is just the value of the function at 5. So, in practice, if we want to find the limit at a of f of x, and we can find a formula for g of x, which is just f with a hole filled in, then the limit of f at a is the limit of g at a, and to find that, we just evaluate g at a. Intuitively, we're taking a discontinuous function and turning it into the continuous function that it should be. To be more precise, given what we said about continuity in the domains of functions, we're finding a continuous function g that's defined at a and is equal to f everywhere else. Let's look at an example. Suppose that f of x is x plus 2 times x minus 1 all over x minus 1. We want to find a continuous function that's defined at x equals 1 and is equal to f everywhere else. In this case, we can find that by doing what you might have been tempted to do right away, namely cancel the x minus 1 terms. This leaves us with x plus 2, which we'll call g of x. The colon followed by an equal sign just means that we're defining g to be equal to x plus 2. And this is exactly what we need. The limit of f at 1 is therefore equal to the limit of g at 1, which by the continuity of g is equal to g of 1, which is 3. There's a video with more of these examples if you want to see them. We didn't prove that g is continuous, but you can verify that it is using the definition of continuity. And in fact, almost all of the common functions we deal with are continuous. Not only that, but when we combine continuous functions by addition or subtraction, the result is continuous. The same can be said about multiplication and division, exponentiation, and even the composition of functions. Remember that we're saying that these functions are continuous on their domains, and we're not saying that the domains don't change. For example, if f of x equals 1, and g of x equals x, then both f and g are continuous. And so is f over g, even though its domain doesn't include 0.